Good afternoon, friend. As in the last two lectures related to ultraviolet visible spectroscopy, we have learned about the properties of electromagnetic radiation, basic terminologies associated with the absorption measurements. Next one, there are some problems in the UV visible spectroscopy. We have already go through it, and there were the four problems in the which are related to the absorption measurement terminologies. Now in the next part 3 lecture, here we are going to learn Lamberts law and associated expressions. Now there are the two main laws in the ultraviolet visible spectroscopy, Lamberts law and Beer's law. Both laws are important. Now Lamberts law deals with the study of thickness measurement of the system. Now if we consider Lamberts law, here its a statement is given. The law states that when a beam of incident light is allowed to pass through a transparent medium, the rate of decrease of radiant power with increase in thickness of the medium is directly proportional to radiant power of the incident radiation. Now here we have already studied some basic terminologies or some basic definitions in UV visible spectroscopy. That is radiant power. The radiant power is nothing but it is a radiant energy per unit time. It is the energy divided by time. That is the radiant power. Now when we consider a monochromatic light, at that time, when a beam of incident light or monochromatic light, when allowed to pass through a transparent medium, that is a solution particularly, or any medium, the rate of decrease of radiant power with increase in thickness, that means there is an inverse relation of the radiant power and the thickness, and the inverse relation the rate of that inverse relation is directly proportional to radiant power of the incident radiation. Mathematically, it can be expressed as minus di by dB is directly proportional to I, where I is the intensity of incident radiation. Minus sign is there that indicates the decrease in thickness with respect to path length, that is a decrease in incident light with respect to path, that is the thickness of the medium, not that. So therefore minus di upon dB is equal to ki, where k is a constant, proportionality constant. If you rearrange the equation, minus di by dB is equal to ki, if we rearrange rearranger kilo, if we rearrange that equation, that I, similar signs, similar symbols, that with respect to I, if we take it on LHS, and dB term, if we take it on RHS, that is we take rearrangement only, minus di by I is equal to k into dB. Here dB is divided term which goes to the RHS and get multiplied to kV. It is proportionality constant. So on rearrangement, that equation becomes minus di by I is equal to k into dB. Now here integrate above equation between proper limits. If you take limits, I is equal to I0 to IT. Here I0 and IT. I0 is nothing but the intensity of incident light, and IT is nothing but the intensity of transmitted light. And B is equal to 0 to B. So the lower limit of B is 0 and higher limit of B is B. So minus sign is there and di by I. So if we integrate, the integration of this term is minus ln I, and the lower and upper limit is given on bracket. Similarly, if we integrate k into dv, after integration we have the term k in bracket b. Now this on bracket term b, here b is there and here 0 is there. 0 indicates the lower term and b indicates the upper limit. So therefore minus is equal to minus in bracket ln I. If you apply upper limit first and then lower limit, we get minus ln it minus ln I0 is equal to k into b minus 0. If you apply this upper limit first and then lower limit, b minus 0, so k into b minus 0 is, so finally it comes to be on RHS side kb. Now this negative sign goes to right hand side, it becomes to minus kb. So ln it as it is minus ln I0. So ln a minus ln b, that can be written as ln a upon b. So similarly the above equation can be written as it upon I0 is equal to e raised to minus kb. So ln it minus ln I0 is equal to minus kb. If we remove the ln, now ln is nothing but natural log, and that natural log if we remove, then at that time on our right hand side we use the term e, and here ln is eliminated. It upon I0 is equal to e raised to minus kb. So here it is equal to I0 into e raised to minus kb, where k is the absorption coefficient. Now here on the exponential factor, k is the absorption coefficient. Now with this equation we can conclude this Lamberts law, only Lamberts law, according to Lamberts law, absorbance of solution is directly proportional to path length, provided that concentration remains constant. Now at that time concentration is kept constant, and A, that is absorbance, is directly proportional to path length. So if we take into account, or if we consider that dB is nothing but the thickness of the medium or path length, we can say I is nothing but the intensity of transmitted radiation. So this is all about the Lamberts law. And with this content, I conclude this session of part 3, belongs to ultraviolet visible spectroscopy chapter. In the next series of this lecture, we will see what is the statement of Beer's law and Lamberts-Beer's law, the combination of Lamberts and Beer's law and its expressions. Thank you very much.